Ionization energy is definitely one periodic trend that you need to get down and of course understand the different exceptions. That's why I'm actually going to be teaching another YouTuber, Melissa Lucy, how to succeed in this topic and of course what you need to know. Plus we'll do different practice problems. So grab your periodic table and let's get started. All right, so the next trend is going to be ionization energy. What that's talking about, it's the energy that's required to remove an electron. And specifically, we're looking at an electron being removed from an atom that's in its gas phase or in its gas state. So like in this case, this originally is just, X is just representing any typical atom. And then this G is telling us that it's in its gas phase. So I know, okay, I'm just literally showing I'm removing an electron and now it's actually going to form a cation. And this is just representing the one electron that I'm essentially removing. So the reason why, by the way, you're going to see this a little bit later on, but this plus one electron, the reason why it's even there and why we're representing it is both of these sides have to balance out in charge. And if this is like a plus one charge and our electron is a negative one charge and this is neutral, so I'm going to say this is actually like 0, then both of those charges have to balance out, plus one, minus one. Combining those two gives us 0. So that's why we have to show that one electron. I don't expect him to have you write this out. I actually just expect you to know the trends, of course, and expect you to know what the actual definition is. So this is what the definition is going to be. So definitely know this part. And then knowing the trend is also going to be really important. So this is where we're completely changing up the trend now. And it's the reverse. It's the opposite of what we were talking about with ionic radius, atomic radius. Now it's where this corner here is going to be like the highest. So everything that we're moving from left to right now across our periodic table, that's going to increase. And now moving up a column, that's where our ionization energy is also going to increase. So something to know is that we can actually remove multiple electrons for an atom, but we only do this one at a time. So we only remove one electron one at a time. Like I can't remove 2 electrons all at once from an atom. It has to be sequential. So in this case, I would start off with something known as our first ionization energy, which is what you're going to be tested on. That's what this trend is actually referring to. So this trend is referring to just one electron being removed. We're only focused on, hey, I'm just removing one electron. This is my first ionization energy. I'm still going to talk about the second ionization energy and kind of like the next ones that come after, just to give you an idea, but you won't be tested on it with the trend, I'd say, but you will be expected to know that, what it means. So our first ionization energy, once again, just means we removed one electron from a neutral atom. So in this case, let's say M is a metal. Okay, we're just representing an atom again. And I'm removing this from its gas state. Well, now it turns into a cation, and I just removed one electron. For the second, let's actually make this a different color. So for the second ionization energy, I'm removing one electron again, but from a cation. So now I started off, it's kind of like where I left off before. Now I'm starting off with the cation, and I'm removing another electron to make it even greater, to make that positive charge be larger. Does that make sense?
Kind of.
Kind of? What doesn't make sense?
I see that it went from, so we're removing, so whenever we remove an ion, then we write, the plus whatever number that was. So is that
whenever we remove an electron, correct?
Yeah, sorry.
Yes.
That's what I mean.
So yes, like I would start off with, this is neutral, right? And then next, because I removed an electron, it becomes more positive, so it becomes a cation. And then now I'm going from this here, M plus, so that cation. I remove another electron, so it's going to make it even more positive. That's where I get that 2 plus. And then if I were to keep going, then I would start off with, if I'm going at the ionization energy, the third one, then I would start off from here.
Okay, I see.
So it's basically where you left off last. And then it would increase again, not magnesium. And that was force of habit. M3 plus 1 electron. And so on, if we needed to do that. Okay. So it is going to be important just to know what this means in case you do see it. But knowing that, I'd say the main thing to know is, one, the trend of the first ionization energy, which is this whole chart. And then the next thing is going to be that it's actually going to require more energy to keep going. So every single ionization energy that you're going to see, like, hey, the second energy is actually going to require more energy to remove an electron. And then same goes for the next one. It's going to be even higher, again, with our energy level to remove a third electron, a fourth electron, and so on. Okay. So I would say the first ionization energy is going to be the lowest energy, and then everything thereafter is going to keep building, and it's going to keep growing. Makes sense?
Yes.
Okay. Cool. Okay, so I'm going to go back just to talk about the trend. So I'm talking about the first ionization energy. All right, so if we were to look at this trend, so I kind of wrote it in reverse here because this is what's typically outlined in like the book and on most exams, I'd say. So the main idea here is just knowing that as we move down a column, if I were to move down this column, it's actually going to require, like, this is actually going to decrease, right? The ionization energy is going to decrease. Once again, just knowing ionization energy is the energy required to remove an electron, right? So this is going to decrease because less energy is required to remove the first electron. So it's talking about valence electrons. So because valence electrons are on the outermost shell, and they're the furthest away from the nucleus, those are going to be the easiest to remove. So those are going to have the lowest ionization energy. And then if we were to kind of reverse this, then I would say, well, if this is going up, then I know that's the opposite here. We're going to have more energy that is going to be required to remove that first electron. And it's not going to follow, what this is essentially saying. It's the opposite. So I would say knowing this way will be important just because of how it's explained. So this is actually talking about the reverse trend where it's decreasing. So decreases. Does that make sense?
Yeah.
Yeah, okay. So now I am going to look at how it does increase for this other trend. So if I'm looking at this one, now I'm saying, okay, well, ionization energy, the first ionization energy is going to increase as we move across a row or across the periodic table from left to right. And I know this because Z effective is actually going to increase. So as I increase my ionization energy, I'm going to increase the Z effective. And what's essentially happening is that basically we're just increasing in energy. So the larger the Z effective, then we know that there's going to be more energy that it's going to take for it to remove, essentially. And the reason for this is because, remember, Z effective is just talking about the attraction with that electron to the nucleus. So if it's so attracted to it and they don't want to split, it's going to take a lot more energy to remove it. So that's why those go hand in hand.
Right. Okay, that makes sense.
Cool. And there are exceptions. Okay. I know.
Always.
I know. Always. Yes, always. But this is why I talk about them. So exceptions to the rule. I went ahead and put the actual, like you might have this on your periodic table where it actually shows you the group numbers, where this is like 1A, 2A, and so on. Knowing these, I'd say, in this case, will be important because there are some exceptions to the rules, as you can see. So it's going to be different when we're comparing something that's in 2A, so the greens, going from 2A to 3A. This is actually going to have a higher ionization energy. So this is actually going to be higher, and this is going to be lower. So it's an exception. It's opposite from what the trend is actually saying. And then same thing goes with 5A and 6A in orange. Well, you would think that 6A would be higher because it would follow the trend. No, it's an exception to the rule. So it's actually the opposite. 5A would have a higher ionization energy, and then 6A will have a lower ionization energy. And I'll explain why. So let's say if I was just to compare beryllium. So beryllium is here, okay? and then I'm comparing boron. So I'm looking at beryllium and boron and seeing why is this exception true? What's happening here? So if I were to try to remove an electron from the neutral atom, that makes it a cation. So it makes it a positive charge. So this is where I start off, right? It's kind of like this idea, beryllium in its gas state. And then next I would just add that positive cation, and then this is one electron. That's essentially what I'm doing. So if I were to write out the orbital diagram here, well, if I have that plus charge, I'm actually removing an electron, right? So I'm removing this. I'm removing that one electron, and that's where I get this new orbital diagram. So what's happening is that this doesn't want, it doesn't want to be alone, I'd say, be split up. Because if we're removing an electron from an orbital that's already full, that's going to actually require more energy to take it away. Mm-hmm. So that's why this would have a higher ionization energy for beryllium right here than boron, because it doesn't require as much energy. So if I were to go back to now boron, I'd see, well, if I'm just trying to take away one electron from boron, then I would take this one. That's already by itself. Like, it's not strong. I'm not actually removing it from a full orbital. And because I'm not removing it from a full or even half full orbital, then I know that's going to require less energy. Okay. And then now if I'm comparing 5A and 6A, let's say if I'm looking at nitrogen. So nitrogen, I don't know if, I highly doubt you could see that tiny little thing. Now I'm looking at nitrogen, which is here, and I'm comparing oxygen. So in this case, I'm going to look at the same sort of orbital diagram again, and I'm comparing nitrogen in its neutral state, and then I'm comparing it to its cation state. So if I were to try to remove an electron here, well, remember that for our p orbital, this is, to fill this up, to be actually completely full, it would go to 6 electrons. To be half full, it would be 3 electrons. So either one of those is going to require a lot of energy from us, because they're essentially, it's stable, it's happy, it doesn't want to be bothered, okay? So if I were to remove an electron from something that is half full, then that's going to require a lot more energy from, let's say, something that wasn't half full. So like in this case, this is actually a little bit more than half full because there are 4 electrons here, right? So if I were to just take one, then this is still half full and it's completely happy. Like there's no problem there. So it wants to either, like, our atoms essentially just want to be half full or completely full.
Okay.
Okay. So knowing those exceptions is going to be, I'd say, the tricky part, because, I mean, there's already so much you have to know. But I would just say knowing that 2A will be higher than 3A and 5A would be higher than 6A. And it is comparing those two to each other.
Oh, okay. I was going to say, so do you think it's smarter to just remember the exceptions or just do the electron configuration whenever you get problems like that?
I would say it depends on, I know you're going to be given a lot of time. If you can just remember the exceptions, great. If for any reason you forget them, write the electron configuration.
Okay, true. That makes sense.
Yeah. So continuing with this, this is just talking about like the next ionization energy. So like ionization energy 1, ionization energy 2, remembering that it's going to require more energy to remove a second electron, a third electron, a fourth, and so on. So if they ever ask you, like which ionization energy is going to be like the highest, well, and they're giving you like, oh, ionization energy 1, ionization energy 2, 3, so on, that the one that is the highest would be the one with the largest number. So like the third one. You know what I'm saying? Right. So that's really it. That's pretty much all you have to know for something like this if you were given a question like that. Let me do one example. So if we're comparing, let's say, boron and I forget this one too. Bismuth. Like there's some that you just don't really see. Bromine is here. And bismuth is here. which one would have the highest first ionization energy?
Just looking at the thing.
Just looking at the trend, yeah.
Which one has the highest?
Highest, yeah.
Bromine?
That's it.
Okay.
Yeah, no tricks here because it doesn't fall under the exceptions, right? We're not going from 5A to 6A. We're not going from 2A to 3A.
Right, okay.
But now let's look at the next one. So if I'm comparing sodium, so sodium's here, and rubidium, which is here, which one would have the higher ionization energy?
Sodium?
That's it. No tricks, okay? There's no tricks here. You're like, you just taught me the exceptions.
I know,
you're not going to throw. Exactly. But that's good to know because now it's time for you to practice. You know, when I was learning this back in college, I definitely felt like, why are there so many exceptions to the rules? Why does chemistry have so many exceptions that are the opposite of what you're actually thinking? And before, you know, you feel overwhelmed or before you think that it's impossible, it's not. Okay, just writing down those exceptions, understanding how to condense all of this together, and really just seeing, hey, I've already put all that information that you need right here. So study this, rewatch this video, and get this down because this will be on your next exam, and I know that you can pass this next exam.